Hi there. Today we're going to do section 4.2, which is composite and prime numbers. So let me pull up the notes. All right. So a prime number is a number that only has itself and one as a factor, and the composite have more than that. So we're going to talk about prime and composite numbers. The following rectangles represent the number 18. The number 18 has 6 positive divisors. 1, 2, 3, 6, 9, 18. So 18 is an example of a composite number because you can get different options to multiply to 18 besides just 18. Find the composite numbers below each number listed across the top. We can find numbers less than or equal to 37 that have numbers of positive divisors. So, I'm so sorry, excuse me. So this is saying 1 only has one divisor, it's 1. 2 has 2 divisors. 4 has 3 divisors, 1, 4, and 2. 6 has 4 divisors, 1, 2, 3, and 6. 16 has 1, 2, 4, 8, and 16. So that's how you read this chart. So this number can be divided by 6 different things. These numbers have exactly 2 positive divisors, 1 in themselves. So these numbers here are the prime numbers. Only can be divided by 1 in itself. These numbers have at least one factor other than 1 in itself. Number is special because number 1 is special. It's neither prime or composite technically because it only has one factor, itself 1. Prime number is any positive integer with exactly 2 distinct positive divisors. And a composite number is an integer greater than 1 that has a positive factor other than 1 in itself. So show that these are composite numbers. So we're using the divisibility rules that we learned last time. So this is an even number, so you know it's divisible by 2, so it's composite because it's going to have 1 and then 1564, and you just need to find at least one other one for it to not be prime. And you know 2 goes in here because it's even. This guy, they have applied the 3 rule, so I add up these guys, I get 9 plus 9, which is 18. 3 goes into 18. So that means that 3 goes into this guy, which means it has at least one more factor besides 1 in itself. So that shows that it's composite. This is the 11 rule, where you sum up the alternate places. So like we added these 2 together, we got 1. Add these together, we got 1. And so 1 minus 1 is 0. Well, it'll go to 0 times. So it's divisible by 11. This guy is even this interesting concept that if I multiply all these odd numbers together, I'm going to get an odd number. And then if I add 1 to any odd number, you're going to get an even number. And every even number is divisible by 2. So that would be a composite number. Composite numbers can be expressed as products of 2 or more whole numbers greater than 1. Each expression of a number as a product of factoring is called a factorization. And then a special kind of factorization where it's down to its prime numbers is called a prime factorization. So each composite numbers can be written as a product of primes in one and only one way, except for the order of the prime factors. So we're going to talk about how to find prime factorization. So, you might have done this in some high school level math. This is called a factor tree. And to do this, you're trying to keep factoring the numbers until you get only prime numbers. And then you can write out this number as a product of its prime numbers. That's called prime factorization. Now, just so you know, this is not the only tree to draw for 84. For instance, I could be like 84 is even, so I know 2 goes into it. 2 times 40, 2. 2 is already prime, so boop, I'm done with that side. 2 goes into 42 because it is also even. So 2 times 21, oh, I'm done with 2 because that's a prime number. And then 21, 2 plus 1 is 3, which means it's divisible by 3. And 3 times 7, these are my prime numbers. So I got the same result, right? 2 times 2 times 3 times 7. So in order to do a factor tree, you just have to think about one factor at first, and then you keep dividing down until you get only prime numbers. These two trees produce the same, so this is an example, but I was talking about how there could be different ways to get to the same end result. We can also determine the prime factorization by dividing with the least prime too, if possible. If not, we turn to the next larger prime as divisor. Once we find the prime that divides the number, we continue by finding the smallest prime number that divides. So this is showing another way to do this. To divide by 2 over and over again until you can't divide by 2 anymore. So then they're like, oh, I can divide by 5. That's another prime number. And then I can divide by 13. So it's kind of finding it similar, but just a different method. How many divisors does 24 have? So this is not prime divisors. This is just how many combinations can you multiply two numbers together and get 24. So I draw mine kind of similar to this, but a little different. I usually say, okay, so we know 1 times itself, and then I go in order. What comes after 1? 2. Well, I know 2 goes into 24 because 2 is indeed, this is an even number, right? So it's 2 times 12. Then I'm like, does 3 go in? Yep, because 4 plus 2 is 6, and 3 goes into 6. So 3 times 8. Now I'm at 4. 4 times 6. And then all I'm left with is 5 in between here, and 5 doesn't go in because it's not 0 or 5. So I know I didn't skip any, because now I can look at these numbers in order. 1, 2, 3, 4, 6, 8, 12, 24. So I know that I got them all. So another way to think of number of positive measures is to consider the prime factorization. So if I break down 24 into with a factor tree, I can say 24 is 2 times 12, 2 is prime. I can say 12 is 2 times 6, and 6 is 2 times 3. So I have 2 cubed times 3. 2 cubed equals 8. It has 4 divisors. 3 has 2 divisors. So we multiply 4 times 2 and we get 8. So that's another way of thinking about it. And this is another way. The number of divisors, if you factor it down to the primes, you take each of the powers and you add 1, and then you multiply those together. So for instance, if I was able, I cannot do a factor tree of 1,000,000. That is going to be not fun, right? But I know that this is 10 to the 6th. And 10 to the 6th, well, 10 is just 2 times 5. And these are both prime numbers. So I know that the prime factorization of this would be 2 to the 6th times 5 to the 6th. Because in the theorem on the previous slide, you can add 1 to each of these guys. Okay, so that's 7 and 7. And then you multiply those together, and that gives you the total number of divisors. So here again, 210 is 21 times 10. 21 is 7 times 3. 10 is 2 times 5. So these are all prime numbers. And then I got my 10, my 10, my 10, my 10. Remember, you're supposed to add 1 to each of those. So that means we're going to have 4 11s, or 11 to the 4th. So this gives us the number of divisors, which that would be really almost impossible to find out by hand. So it's helpful to know this theorem. To determine if a number is prime, we must check only divisibility by prime numbers less than the given number. For example, to determine if 97 is prime, we try dividing 97 by prime numbers, 2, 3, 5, etc., as long as it's less than 97. If none of these prime numbers divide 97, then 97 is prime. Excuse me, should the piece of prime number greater than 7? P divides 97. The 97 divided by P also divides 97 because P is greater than or equal to 11. Then 97 divided by P must be less than 10 and hence cannot divide 97. If n is a composite, then n has a prime factor p such that p squared is less than or equal to n. If n is an integer greater than 1 and not divisible by any prime, p such that p squared is less than or equal to n, then n is prime. Okay, what does that mean? This is an example. So basically, if you're trying to figure out, is this number composite or prime? and you try to do the different tricks, like, is it even? No. If I add that 9 and 3, that's 12. 12 and 7 is 19. That's not going to work by 3. Okay, let's try 4 is not going to work. 5 is not going to work. It's not 5 or 0. 6, it's not divisible by, it's not even. 7, I don't know. So you might kind of get stuck if you keep on trying to think through this. Well, let's say you don't have to think through all the primes. You just have to think through the primes that are less than, where p squared is less than 397. So basically you can stop at 19 because 19, if I had 20 squared, that'd be 400, right? So I get to stop at 19. So I can check only these numbers, 2, 3, 5, 7, 11, 13, 17, 19. And then I don't have to keep on going. I don't have to keep going forever because I know that once I've gotten to something where I'd have to squaring this number would give me something greater than this product, it's not going to divide in there. So 19 doesn't go into 397, so that means this number is prime. Like all the numbers, all of those numbers leading up to 19 don't go in. Is this composite or prime? Well, I think through the prime numbers. So it's good to kind of know the prime numbers, right? You have 2, 3, 5, 7, 9, then 10, 11, then 13, etc. Now, if I square 9, I get 81, right? Oh no, 9's not a prime number. Sorry. 9 is 3 times 3. I don't know why I wrote 9. Sorry about that. Brain lapse for a second. 11 squared is 121. So I can stop. I don't have to go to here because p squared needs to be less than the number we're talking about. So I just have to try these guys. So does 2 go in there? No, because it's not even. Does 3 go in there? No, because 9 plus 1 is 10, and that's not divided by 3. 5 does not go in there because it does not end by 0 or 5. But then we can try 7. Does 7 go into 91? It does. It's 7 times 13. So then I'm done. I don't have to keep going. One way to find all the primes less than a given number is also to use the seed of Eratosthenes. If all the whole numbers greater than 1 are considered, the numbers that are not prime are methodically crossed out. So it's basically just crossing out the numbers, all right, that are not prime. So you're left with only the prime numbers. This is another way to think through something's prime. It's one of the ones that are left here, right? You're crossing out the other ones that have factors of something else. So that's a little bit about prime and composite numbers. Hopefully that was helpful. As always, please reach out to me if you have any questions.